Welcome back, class. Good to be with you. We're going to do Whitlock and Schluter Chapter 10, the normal distribution. We'll do it in two parts. First one will be more on the theory side. The second one will be some examples. All right. Now, normal distribution is one of my favorite parts of the whole course. And so I'd like to start off with Romans chapter 1, verse 20. Since the creation of the world, God's invisible attributes, His eternal power and divine nature have been clearly seen through what has been made, so that they are without excuse. I submit to you that the normal curve is one of those things that the Lord has put into the world that gives an order and a structure that underlies things that is profound. And when we see this, we are able to see something of His creative genius, His ordering properties in the world. And I want to try to unpack that not only today, but throughout the rest of the semester. So let's start off with our normal distribution here. It is very aptly named. It's the only probability distribution which has come to be sort of the default. That's why it's called the normal. It's the benchmark. Things are weighed against it. Now, we have special notation using the notation for probability distributions. If x is normally distributed, we write this tilde sign, and again, that means follows the distribution. So we'll say follows a distribution, in particular, normal. And it has two parameters. The first parameter is the mean. The second parameter is the standard deviation. Okay, so mean. It's the only distribution which is parameterized by a simple shape and then a center and then a spread parameter. The other ones just don't have that. You'll think of the binomial parameters were n and p. We can find the mean and the standard deviation in terms of n and p, but the parameters themselves were not n and p. Were not mean and standard deviation like they are for the normal. So this in and of itself is something that's special. Okay, now we've got the basic form here. Now we won't focus in on this, but here's the function, and I'll talk a little bit about its history in class. There it is, folks. Notice there's a square root of pi inside that function. Remarkable. Where would we get this square root pi coming in? This is truly amazing. Now, I'd like to share three simple examples for illustrative purposes. Let's do the first one as the U.S. adult male height. So first, probability distribution. I'm just going to sketch a nice little bell-shaped curve here. And the center is 70 inches. So males in the U.S. on average are 70 inches tall. And the standard deviation is 4 inches. One standard deviation away takes you to this point here, which is a special point. It's called the inflection point. You'll notice that we have this downward cupping motion, and then we switch to an upward cupping motion. That point of transition there is the inflection point. And so you can always sketch that very easily on your curves, one standard deviation away. Okay, I'm going to go ahead and do two standard deviations just to fill out the graph. 70, 74, 78. Take it down here to 62. This is the distribution of heights of U.S. males. Now, it turns out, and we'll comment on this later, that exactly 34% of the males are going to be between 70 and 74 inches tall. The distribution is symmetric, so 34% are between 66 and 70 inches. Again, 14% are from 74 and 78, that is one standard deviation above the mean, two standard deviations above the mean, and we're symmetric, so it's 14% from one below to two below as well. Okay, let's contrast that with the female heights. Let's do females, different color here. Their mean is 65 with standard deviation 3.5. So I'm going to go ahead and sketch the curve. Same exact shape. If I could copy that shape, just boom, pop it over, I would. And so their center, though, is 65 inches, and their standard deviation is 3.5. So I'm just going to go 68.5. And that's one standard deviation up. Going down here, we'll have 61.5. And again, 34% of the data is within the first standard deviation above and below. If you go 2 standard deviations, we'll go up to 72. We'll go down here to 58. And that'll be good. Now, it turns out that IQ scores also follow a normal distribution. Let's do those in green. IQ scores. Their mean is 100, standard deviation is about 16. So we have 100 in the middle, and then I'll go 1 standard deviation up. You know, let's just make that a little wider, just to show the spread a little bit more. 116. And you'll notice the arbitrariness of that draw. We're not looking for a perfect sketch here. We're just looking for a diagram that gets things in approximately the right proportions. When they're in the right proportions, then our eyes can help us come up with the right basic relationships results. Okay, so 16 down, 68 here. Okay, again, I've got my 34, 14. Now, with these 3 distributions, let's look at their properties. Okay, properties of the normal curve are that they all have the exact bell shape, they're symmetric about the mean, and the median, you'll notice if you add up the area on the left, it's going to be the same as the right, so the median is equal to the mean, and that's also the high point, which is the mode. I have down here 34-14-2 rule, which is also known as the empirical rule. You'll read that term in your book. Now, the way the book connects it is, I'm going to erase this, but the book is going to say, well, we've got approximately 68% of the data within 1 standard deviation. And then if you add up these guys here, you're going to have 96%. And if you do a rounding, we go to 95% within 2 standard deviations of the mean. Now, what things follow these? Well, as you can observe, I want to take a look at a figure 10.1-3 in our text. He's got us with body temperature, it's approximately normally distributed, brain size, number of bristles on 4th and 5th segments of abdomens of fruit flies, and it just turns out that many things follow this approximate bell-shaped curve in the world, but that's not all. Besides measurements, it turns out that accumulations of random events tend to a normal distribution. For example, gambling phenomena. That's actually how the distribution was first developed and discovered, was through a pursuit of how to express these gambling phenomena that the binomial distribution became too unwieldy to. Errors in measurement or target shooting. If you've got a target and the shots are boom, 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 they're all around here, well, when you take the bullseye, let's just stick it in the middle, and you measure these distances, all these green lines, when you put those all in a histogram, you're going to go approximately normal. And lastly, well, before I do lastly, there's one more I want to add. I want to add many distributions. Okay, otherwise known as limiting distributions. For example, if I go to good old RStudio, now in the Math318 biostat file, I have scripts for this. And this is the graph that I've come up with. Here's a binomial probability distribution with n equals 20, and there are multiple choice questions on an exam, so they were 0.2 probability of getting them correct, so p equals 2. You'll see that this isn't quite normally distributed with n equals 20, p equals 0.2, but as n gets larger, take a look at this bell-shaped curve superimposed. Looks pretty good here, and once you're rather large, it's fantastic. Yes, it's true, this is a skew-right distribution, but the tail is so small on the right as to be almost nothing. Similarly, with a gamma distribution that looks in appearance like a chi-squared, and the same thing happens with a chi-squared. It's a skew-right distribution, so I get this green guy, and as the parameters of it gets larger and larger, a normal curve approximates it very, very well, and in the limit is equal to it. Lastly, sample means. I'll demonstrate this later on, but means themselves, no matter whether they are means of light years it takes for the light from stars to reach the Earth, or the distances of electrons between one another inside of a molecule and everything in between, means themselves are approximately normally distributed and tend to a normal distribution. And those are super, super important to us. Okay, let's take a look a little bit more detail. There's a thing called a standard normal distribution. Now the standard normal distribution goes like this. You've got 3 examples of normal distributions: heights, males, females, IQs. How can I get these exact probabilities here? Well, we could calculate them all individually, but that's going to become really tedious, and when you tabulate your results, you're going to have a lot of tables. So instead what we do is we come up with a convention. Let's count the number of standard deviations away from the mean, so that in the middle you're at 0, and then if you go up 1 standard deviation, we'll just call it 1. If you go up 2, you'll call it 2. So we have a 0, 1, and a 2, a 0, a 1, and a 2. This is the z-score, the z-axis. And it is a standardized, so it's the same thing between each distribution. The probabilities are the same throughout. The shape is identical throughout. The only thing that's changing is the mean and the standard deviation. So we can standardize that using the following formula. Z-score equals statistic minus parameter divided by standard deviation. You can think of that, if you want, as just taking this whole curve and shoving it to the left so that these guys all subtract 70. And if you were to do that, then you'd have a -8, a -4, a 0, a 4, and an 8. Now, if we just divide them all by the appropriate standard deviation, which is 4, right here, then we're going to get the values that we had on the original z-score axis. And so that's basically how it works. So to review that, you just take whatever the specific z-score you're running, or excuse me, the specific value you have, you subtract off the true mean, and then we divide by the standard deviation. that gets it for us. Okay, I have that replicated right here, and when we do, we call that a z-score, and it's normally distributed with mean 0, standard deviation 1, given that our x is already originally normally distributed. If x is not normal, then z will not be normal. Okay, but you could still calculate a z. Now, all of those have in common this 34, 14, and then the remaining 2% is hanging out on the right and on the left. And I'd like you to memorize 34, 14, 2. Those three numbers for the probability distribution will be very valuable to just have at your fingertips. Okay. For an example, we've got Aaron and Miriam, two basketball players, 78 and 73 inches tall. Okay, great. We have a male and a female. Now, question. Relative to their sex, which player has the greatest height advantage? Obviously, Aaron is taller, but is he relatively taller than the guys, or is Miriam actually relatively taller? One way to answer that question is using their z-scores. So the z-score for Aaron is going to be 78 minus the male mean, which is 70, divided by the male standard deviation, which is 4. So Aaron comes in here at 8 over 4, which is 2, whereas Miriam comes in at 73 inches tall, 65 mean, with a 3.5 standard error. So she is 8 over 3.5, which is 2.29. So if I come back to the map, I refer to these distribution pictures as maps, then Aaron lines up right here on the curve, whereas Miriam actually comes in over here at 2.29. So Aaron is sitting here at the 98th percentile of the distribution. That is, he's taller than 98% of guys. There's only 2% that are taller than him. Miriam, by contrast, is somewhere above the 98th percentile. Now, just a word on percentiles. -2 z-score is at about the 2nd percentile. It's greater than 2%. It's below 98%. -1 is 2 plus, we'll round this again to 14. Okay, 2 plus 14. That's at the 16th percentile. And then 0 is at the 50th percentile. That's the median, as we said. 1 now is all of the preceding plus the next 34%. So 1 standard deviation above the mean is the 84th percentile. 2 standard deviations above the mean is where Aaron wound up at the 98th percentile. Okay, now 3 is 99 point something percentile. How can we get the specifics? We'll cover that in the next section.